Hello, thanks for joining my talk. It's my pleasure to talk about a project Ivan Lobato, Sandra Vannaut, and myself have been working on about the restoration of STEM images using neural networks and how that impacts the quantification of atomic structures. Now, first off, let me clarify what I actually mean by image distortions. So we have a variety of distortion in STEM images, starting with the omnipresent Poisson noise and thermal noise, and also scanline distortions such as X and Y jitter and fast scanning distortions, and some others as well. So we would actually like to restore these images and correct for all these effects in just a single go. And if we try to attempt this in a classical manner, this turns out to be extremely difficult, because one would actually have to identify, localize, and then correct each of these effects individually. We're trying to do just that by using convolutional neural networks instead. So the problem with machine learning, though, is that we always need some labeled ground truth data. And this is, of course, impossible because we cannot record undistorted data. Furthermore, we're limited in the sampling of materials we have with experimental data, and therefore we're basically stuck with having to model our own data and create synthetic data sets to train a neural network. So the general idea here is we'd start looking at experimental data, then try to model those images as good as we can, then generate synthetic data sets and use those to train a convolutional neural network. But we can actually do a bit better than that. With our first trained model, we can then go back, use experimental data, feed that into the convolutional neural network, and see if the result is what we expect. So if it turns out that we get artifacts or we have some distortions left in the restored images, we can go back and improve our modeling and retrain the neural network. In this way, we do not only improve our restoration results, but we can also improve our understanding of these distortions and improve the modeling as well. So if we do that, we end up with a convolutional neural network that performs pretty well on experimental data, as you can see in a few examples shown here. But we're not only interested in having nice images, we also want to quantify atomic structures. To check whether that works out as well, we actually designed a study to check if we get an improvement also on the quantification of atomic column positions and their scattering cross-sections. And in this way, we can also check the influence different distortions have on these quantifications. So the study is as follows. We'd start off by creating different models, then run a full multi-slice simulation, apply these model distortions, restore the images, and then determine atomic structures on both the raw images and the restored ones and compare them to ground truth values. We created a variety of models for this study, each of which has some sort of peculiarities, such as dislocations or twin boundaries and things like that. On those models, we would run a full multi-slice simulation using Multem with a frozen phonon model, and then apply these distortions. Now we were looking especially at distortions we believe to have the biggest impact on the quantification of atomic structures, which is X and Y jitter and Poisson noise and fast scanning distortions. Now let me elaborate a bit on how we model those distortions. First off, the X and Y jitter are basically scan line shifts in the X and Y direction. Mathematically, they can be described in the same way by a series of related terms. In this mathematical representation, we have two parameters we can play with. That is the sigma parameter and the phi parameter. So the sigma parameter basically causes a short range effect. It's basically a random offset with a normal distribution. And the phi parameter couples each value to its previous value in the series. So that creates some sort of long range effect. And what that looks like you can see here. So in the center here you basically see such a generated profile, and you would then shift each scan line in this image corresponding to this offset in this profile, and then you would get a distorted image like you see here on the right. And the impact these different parameters have, I can show you in a little simulation here. So on the left side you see the basis model. In the center you see the raw image, distorted. On the right hand side the restored version of it. So here we're now playing with the phi parameter of the X jitter. And there you can see that when you increase this parameter, you can see that the atoms actually start to sort of wobble in the X direction. So that's this long range effect I was mentioning. The sigma parameter acts on a short range, which means it doesn't so much shift the entire atomic columns, but it distorts it on a local level and tears it apart, as you can see in the center here. So and the same goes for the Y jitter, just in a different direction. Here again the long range parameter. As you increase that, you can see that the atomic columns wobble up and down. The sigma parameter quite similarly acts on a more local level. There you see the atomic columns sort of stretching out and squishing together on a more local scale. Now, the fast scan distortion arises from a finite detector response time. So basically, when the beam scans too fast for the detector to pick up, this results in a smearing out of the signal along the scan direction. And that can be described as a convolution along the scan direction with an exponential decay function. Now, as we increase the severity of this effect, one can see that the atomic column features smear out towards the right. That also leaves a very characteristic mark in the Fourier space, as you can see here. Then we would restore these images, and eventually we determine the atomic structure parameters by fitting Gaussian functions to each atomic column using the StatStem toolbox. So by having these Gaussian functions fitted, we can extract the parameters of the atomic column locations and their intensity and width. And from the intensity and width, we can calculate the scattering cross-section, which is essentially the volume under the Gaussian peak. First off, we wanted to see how much we could actually gain by just denoising the images. For that purpose, we reproduced a study our colleagues had done some years ago in the original paper on the StatStem toolbox. There, they simulated a platinum crystal through thickness, and in that way generated a series of signal-to-noise realizations. They then quantified the error on the x coordinate of the column positions in the central column and on the scattering cross-section of this column. And they had shown quite nicely that even with raw images, they could reach the theoretical lower bound on the variance for both the atomic column position and the scattering cross-section, which you can see here on the right. So we reproduced that exact same study with 4 different noise levels and plotted those over the crystal thickness as seen here as well. So starting with the highest dose setting, there's actually not much difference comparing the convolutional neural network results with the raw data. But as we decrease the dose 1 order of magnitude, we see a slight shift. If we decrease it another order of magnitude, we're actually starting to see deviations and already passing this lower bound on the variance. And reducing the dose even further, we actually see a quite significant improvement even by only just denoising the images. Now that is all only results on the variance of these parameters, but let us move on to a somewhat more practical example. In this example, I chose a platinum crystal in the 112 zone axis orientation with a dislocation. I introduced a dislocation to make sure the neural network doesn't pick up only on periodicity of the crystal, for example. Let me start by looking at the influence of the fast scan distortion. So on the left-hand side in the black box, you can see a distorted image with a heavy fast scan distortion. And in the orange box below, you can see a restored version of that image. Correspondingly, in the left graph, you see the mean absolute error on the atomic column positions. And on the right-hand side graph, you see the mean percentage error on the scattering cross-section. Now you can see that for the raw images, the error on the position increases as the severity of the fast scan distortion increases, but with the restored version that's been mitigated quite well. Also, we see some improvement on the scattering cross-section with the restored versions as well. Now looking at the long-range parameter phi for the white jitter distortion, you can see that as the severity of this effect increases, also the error of the atomic column position especially increases, which is to be expected as you've seen before. This effect basically shifts the entire column up and down. That doesn't so much affect the scattering cross-section accordingly because the actual shape is sort of preserved. But also here we see significant improvements for the restored versions in both the position and the scattering cross-section. For the sigma parameter of the X jitter distortion, we can see an almost linear dependency of the error on the sigma parameter for the atomic column position determination, and a somewhat less pronounced impact on the scattering cross-section. Also here we see significant improvements for the restored versions. Of course, in practice we don't have these distortions in that isolated fashion, but we'd have a mix-up of all these distortions at the same time. So if we look at such an example, we can see how powerful this restoration can actually be. So on the atomic column position, we can see here that for such an example, we can gain about 0.015 angstrom in the accuracy for determining the atomic column positions, and roughly 4% in scattering cross-section. And that of course translates directly into an improvement in the accuracy for example atom counts. And with that, I'm at the end of my talk. I want to thank my collaborators on this project, Ivan Lobato and Sandra Van Aert, and also thank you to all my colleagues at EMIT at the University of Antwerp. Thanks a lot.